Everyone, what we're going to do today is go over experiment 1, measurement, volume, and density lab, and then you guys are going to do the rest of the experiment. So I'm just going to go over some background information about the experiment first. So in experiment 1, what we're going to be doing is we're going to be taking a aluminum cylinder that's shaped like a cylinder, and what we're going to do is we're going to find its density. So density is defined as mass divided by volume. So we're first going to be finding the mass in the first part of the experiment, in part A, and the only way to find the mass is to just weigh your substance on the balance or on the scale. And then in parts B, C, and D, we're going to be determining the volume of our cylinder using 3 different methods. So there's only one way to find the mass, but we're going to use 3 different methods to find the volume. And then after determining the volume in each case, we're then going to plug it into this equation and determine the density. And then we're going to, at the end, compare the densities that we determined for a cylinder. Theoretically, all those values should be the same, but we're going to compare and see how different they will be from each other. So in the first part of the experiment, we're going to be finding the mass of our aluminum cylinder using a digital balance. Digital balances come in different shapes. The one that we have in lab, some of them look like this, and some of the other ones look like the one here. So I'm going to go over this one with you guys first. So each of the balances has an on-off button. So if it's turned off, you just press it and you wait for the display to reach 0. If it doesn't reach 0, you press the 0 or the tare button. On a lot of our balances, those are actually 2 separate buttons, okay? So 0 means that if there's nothing on that scale, then we want to set a baseline, and we want that baseline to be 0. So when there's nothing placed on top of the platform for the balance, you press this 0 button, okay? The tare button, what it's used for, is let's say you want to weigh some powder, let's say inside of a container, okay? And I just want to find the mass of my powder, but I can't just pour my powder on top of the platform on the balance. I first have to put my container on there, okay? And then I can put my sample inside of my container. Now, if I want to subtract the mass of the container I'm using, I just place my container on top of the platform and I press the tare button. And then the display will read 0. So the tare button subtracts the mass of your container for you automatically so that you don't have to do that yourself. So it saves you an extra calculation. Otherwise, if you don't press the tare button, okay, you weigh your container first and then you put the powder in there and then you subtract the mass of the container from the mass of the powder plus the container, okay? All right, and then a lot of the balances have this little balance symbol that tells you when the balance is stabilized so that you can record the mass that's on the display. In our class, we're going to be using the International System units, so just make sure that the units will be in grams. And our balances always give us our mass to 3 places after decimal. So keep that in mind. Anytime you'll be recording any masses in this class, it should have 3 numbers after the decimal, okay? Now, before the decimal, it could have 0 numbers, it could have 1, 2, or 3 numbers, but after the decimal, there should always be 3 numbers. Sometimes, because these balances are pretty sensitive, they fluctuate a little bit, the last digit especially, so you just try your best to put the best answer down, okay? All right, so in the first part, and notice what I'm going over with you guys is sort of like a procedure of what we will be doing in this class. So that gives you an idea of how to write a procedure. So we're going to 0 the balance first, and then we're going to take our aluminum cylinder, put it on the balance, and we're going to make 3 measurements of it. The reason we do 3 measurements is because we want to make sure our answers are reliable, okay? We want to make sure that they're reproducible, and if they're reproducible, that means that they're reliable. So reproducible means that every single time we measure the same mass on the same instrument, it should give us pretty much the same number. If it's off by a tiny little bit, it's not a big deal, but it should give us very close masses every time, if not the same mass. Okay, then we're going to calculate the average, and then we're going to calculate the deviation from average. The deviation from average is always a positive number, and it's whatever you got for that trial value, the value that you got for that trial minus the average value. So you take your three masses, right? You average them, and then you take the first mass, you subtract it from the average. Take the second mass, subtract it from the average. Third mass, and subtract it from the average. The deviation will always be positive. Even if you get a negative number, you just ignore that negative number. Okay. Now I also want to tell you guys something about the average. When you calculate the average and you add up all the three masses of your measurements, okay, the sum might give you more significant figures than what each of the individual trials had. So then when you divide by 3, because you're making 3 measurements to find the average, remember the 3 will have infinite significant figures, okay? Because the 3 indicates that we did the experiment three times. So for example, let's say I have a mass of 7.000 grams as my first trial. Let's say I had 6.998 grams as my second trial. And let's say I had 7.002 grams as my third trial. So when I add these three numbers up to find the sum, this will give me 21.000 grams. Notice that my answer has 3 numbers after decimal because when I added them, I have 3 significant figures. Now, to find the average of these 3 numbers, I would take the 21.000 and divide it by 3. This 3 here has infinite significant figures because it's referring to the trials that we did, right? So we did trial 1, trial 2, trial 3. It's the number of times we did the experiment. So the 3 has infinite significant figures. So you might think then your final answer should have 5 significant figures because of the sum. And in regular calculations, we would apply those rules. But in this case, I want you to know that our answer can only have 3 places after the decimal for our average. The reason is that your value for the average can never be more accurate than each of the individual trials because you can't get a number that's more accurate than the instrument that you used. Okay, so our final answer for the average will only have 3 significant figures because it can only be as accurate as each of the individual numbers that we had. So then if I were to find the deviation for this first one, then it would be the 7.000 grams, right? That's the trial value. That's this number here minus the average value, which is in this case actually also the same thing. It's in absolute values, right? Which means my answer will be zeros. Even if the calculator gives you a negative number, you just ignore the negative number, okay? And that's what these absolute values here mean. These lines here on this side and this side, these numbers are absolute values. Okay, so then in experiment 1B, part B, what we're going to be doing, so now we found the mass, we found the average mass, and then what we're going to be doing in the next part, in part B, is we're going to be finding the volume. This time, in order to find the volume of our cylinder, we're going to use the equation for the volume, which is pi over 4 times the diameter squared times the height. I want you to know here also that this number 4 has infinite significant figures, okay? And the pi, remember pi is repeating, 3.1416, and it goes on and on. So our significant figure value will be determined by the diameter and the height. The diameter is the measurement all the way across here, and the height is this height over here. Again, we're going to be taking 3 measurements, and we're going to be averaging those values, taking the millimeter values and converting them to centimeters, and then plugging it into the equation to find our volume in units of centimeters cubed. Okay, so keep that in mind that you're plugging in the average centimeter values for the volume. Then once you find the volume, you can now find the density using the mass from the first part and the volume that you just found in the second part, part B. Okay, so in order to find those dimensions of height and diameter, we're going to be using something called a vernier caliper. A vernier caliper does the same job as a ruler, except it's more accurate than a ruler. So the way that a vernier caliper works is that it has two jaws right down here. We use these external jaws and we put our object here. So first we completely shut this, close this completely, press the 0 button on there, again to set up baseline, okay? That tells us that when these two are connected to each other, right, the distance between them is 0. So that's why we press 0. Then we put our cylinder right here between this bottom external jaw and we record the number on the display. And that value, again, will be in millimeters. Okay. So just like this, except we will have our aluminum cylinder. Our object will be our aluminum cylinder, and we record the value that the display gives. Okay, so I would like to go over two terms with you guys, extensive property and intensive property. So extensive property are those that depend on the amount of substance. For example, mass and volume. So if I am weighing, let's say, a piece of rock, okay, if I cut my rock in half, its mass will also be cut in half. If I cut my rock in half, its volume will also be cut in half. So mass and volume are extensive properties because they depend on the amount of sample that we have. If that amount changes, then that property changes as well. Okay, so extensive depends on the amount of sample. Intensive properties are independent of the amount of substance that we have. Okay, so for example, color is an intensive property. I always think of intensive for independent. So if I take my rock and I cut it in half, for example, its color doesn't change, it stays the same. So color is an intensive property. Same thing with density, okay? So if I take my rock and I throw it in water and it sinks, if I take that same rock and I cut it in half and throw it in water, it'll still continue to sink. If I cut that in half, it'll still sink. So density is an intensive property. It doesn't depend on how much of the sample we have, just like how color is an intensive property. So if a substance is going to sink, it doesn't matter how much of it we have. It'll continue to sink regardless of the amount. And so density is an intensive property, okay? Other things are like boiling point and melting point. Water always boils at 100 degrees Celsius. It doesn't matter if you have a cup of water or you have a big pool of water, they'll both always boil at 100 degrees Celsius. So boiling point is an intensive property. It's independent of the amount of sample. So what we're doing in part C is in part C, we're finding the volume of our little aluminum cylinder again. Remember that in part B, we found the volume, but what we did is we used external dimensions. We used the diameter of it and we used the height of it to find the volume by plugging it into the volume equation. In part C, we're also finding the volume again, but this time we're going to be looking at the volume of our object or determining the volume by the amount of water that it displaces. So the objective of part C is to find the volume and the density of our cylinder, okay, by how much liquid it displaces in a graduated cylinder. So what we do is we take a graduated cylinder, fill it up about halfway with water, record the volume of the water in there, and then we submerge our cylinder inside of it, and what's going to happen is that the level of the water is going to come up. The difference in this level, the amount that the level of the water increases by, is equal to the volume of our object. In this case, that'll be our aluminum cylinder. So the final volume of the water plus the object subtracted from the volume of just the water by itself in the graduated cylinder gives us the volume of our object. So this is another way of finding the volume of the object. So in part B, we found the volume by plugging it into the equation. In part C, we're finding the volume by the amount of water that it displaces. So we've already looked at how to read the volume in a graduated cylinder. Remember that when you read the volume in a graduated cylinder, it has to be at eye level. Your graduated cylinder has to be on a flat surface at eye level. And we read at the bottom of the meniscus. And we said the meniscus is this curve, right? The meniscus is this curve because the water is attracted to the container it's in, so it kind of travels up the sides of it. So we read at the bottom of this downward curve, okay? Our graduated cylinders have an error of plus or minus 0.5, which means that we can read them to the correct significant figures within 0.5 milliliters, okay? And remember, 0.5 milliliters is the same thing as centimeters cubed. Now, what that means is this last digit is either a 0 or a 5. And remember that we can always read one past the markings. So here you can see each of these markings is 1 milliliter, right? So here's 20, 21, 22, 23, 24, 25, and so forth. Each marking is 1 milliliter. 1 is to the ones digit. That means I can read to the tenths place. So I can read 1 past the markings. So here you can see here's 30, 35. The meniscus is between 36 and 37. So it's 36.5 milliliters. If it was directly on the line of 36, then it would be 36.0. Okay, so if it's exactly on the line, you have to write the 0.0 at the end for the graduated cylinders because that will show that there's that extra significant figure there. If you just write 36, that's just 2 significant figures. But if you write 36.0, that's 3 significant figures. So remember, always read 1 past the markings in a graduated cylinder. Okay. So then what we're going to be doing in part D is we are going to be again determining the volume of our cylinder, but we're going to be using a different method, okay? So when we place an object in water, this is just something I want to point out before I go over part D, there is a downward force on the object due to gravity. But when something is submerged in water, there's also an upward force called the buoyant force. That's a force that's placed on the object by the water. So if you've ever been inside of a pool, you notice that your feet always want to float upwards. Okay, it's hard to just stand up straight in the water, right? Your body keeps wanting to push up because the water underneath it is pushing up on it. Okay, so that is called the buoyant force. So what we're going to be doing in part D is we're going to be again determining the density, or first the volume of our object, right? We're going to be determining the volume of our aluminum cylinder. Remember that what we said in part C is that if our cylinder is submerged in water, it brings the level of the water up, right? And the volume of the water that comes up is equal to the volume of our cylinder, right? That's how we determine in part C what the volume of our cylinder was. So in part D, we're going to be doing the same thing. We are going to be determining the volume of the water that comes up here. Okay, so when the cylinder is placed in water, the amount of water that comes up, that volume is equal to the volume of our object. And that's what we're trying to determine in part D. So now, in order for us to determine this volume, remember that density is equal to mass divided by volume. Okay, so what we're going to first do is we're going to first determine what the mass of this water here is. Okay, now it turns out that the mass of this water is equal to the mass of our object in air, which we determined in part 1, right, that average number that we're going to get in the first part, part A, minus whatever the mass of our object is when it's submerged in water. When I submerge my object in water, its mass actually decreases because of that buoyant force. So our balances have this little thing at the bottom of them that allows us to to get the mass of our object when it's submerged in or hanging in water. Okay, it has to be the hanging mass. So once I determine that hanging mass, I plug it into this equation here, and I take the mass that I found in part A, that average mass, plug it in here. I take the difference between those two, and that gives me the mass of this water part right here, the amount that it came up by. Okay? If I plug that mass into the equation for density, and I plug in the density of water, that'll give me the volume of that water. This density is a constant number. There's a table in your lab manual that gives you the density of the water at different temperatures. So I'm going to find the temperature of my water. I'm going to look up on that table to see what that density value is. I'm going to plug in this mass in here, and that gives me the volume of this water up here, which is equal to the volume of my aluminum cylinder. So then I can just take the same density equation we've had, plug that into that density equation, the mass of the object, that's from part A, okay, divided by the volume that I get up here, and that gives me the density of my object again. Okay, a different way of calculating the density. Okay, so the equations that are given in your book for this part are a little bit confusing. So I would like you guys to use this equation over here, okay, to find the mass. And remember, the buoyant force, the buoyancy force, is the mass in air minus the mass in water. So when it asks you in the calculation section to determine that, you just take the difference between these two. Okay, that's the buoyant force. And then to find the volume of your object, you just plug it into this equation over here. And for density of the water, you're going to look that up based on the temperature you're given. You're going to look it up on the table. Okay, and then you'll determine the density using the mass in air and the volume that you find here. Okay, and then use the error and percent error, and those equations are given to you in your lab manual. The true value for the error and percent error will always be the same, the 2.702 that's given in your lab manual. That you're going to use that for each part because it's the same cylinder. The true value is the correct value, is the expected value that we should aim for. Okay, the experimental value is the value that you got here that you calculated in this experiment. Okay, so now I went over the background with you guys. Now before watching the video or before doing the experiment, you have to set up your pre-lab. Remember that for pre-lab, you're following the instructions that are given in your lab manual right underneath the title. It says pre-lab. You're going to follow these instructions here. For this experiment, it's a little bit different for the pre-lab, but you're first going to write down the objective for each part of the experiment. So objective A, B, C, D. Okay, so for each part, write the objective, which is what the purpose of the experiment is. Then for the background section, you're going to define the terms that's given in your pre-lab section in the experiment 1. So right over here, it'll tell you which terms to define. Okay, you're going to find the definition of those terms, and then you're going to briefly outline the procedure. Okay, now remember, the procedure should be detailed enough so that the person doing the experiment can follow your instructions without using the lab manual. But it should be brief enough where you're not copying everything from the manual. So I gave you guys some examples as I went over this experiment with you. That's kind of like how you can do the procedure. And then afterwards, I'd like you to set up the data table. The data tables are also given in your lab manual, but you can, I also put them here so you can just copy mine in your on your paper in your notebook. Okay, please make sure that they're organized clearly. Okay, so I gave you part D as well, pre-lab or the data table for part D. Remember that the data tables are the measurements that you make in lab. Those go in the data tables. You should always record all the numbers in the data table and also include units. Don't just put the number down. Make sure to include units for each of the things that you'll be recording. So as you do this experiment or you go through it, you will be recording your data on these blank lines for each part. Okay, so I just want to go over a sample pre-lab and a sample kind of an in-lab with you guys really quickly. So here is sort of how you would do a sample pre-lab, so objective, what the purpose of the experiment is, to find the volume of the aluminum cylinder and use the mass from part A to calculate its density. So I'm kind of going over part B of the experiment and how you would sort of write the pre-lab for it. Here's an outline of the procedure for it. So notice that I'm taking that big paragraph that was written kind of in an outline format, condensing it, but you can still follow my procedure to do the experiment without having the manual. And then for the in-lab portion of it, the data table that I had, I recorded the measurements that I got for the initial and final volume, and then I did the calculation. So for the volume, right, it was the final minus the initial, and I put the answer here. The density, notice I wrote the equation, I plugged in the numbers, I put the pre-rounded number and then the final rounded answer with the unit, and I boxed the final answer. Okay, same thing with the error. And remember, the error is always a positive number, and error has units as well. It's whatever the units of the measurement were. And then for percent error, again, same thing. I put the pre-rounded number, the final rounded number. Notice that percent does not have units. It's just the unit is just percent. Okay. And then I wrote the results. My results are the answers to my calculations. So all the answers that I had boxed here, I put them in the results table. And then you also make sure for the conclusion, you do a discussion as well. And for the discussion, just make sure to write a well thought out discussion where you analyze your results, write down what the results mean, and also discuss the sources of error that were present. Carelessness does not justify as a source of error. Mistakes in calculations does not count as source of error. So sources of error are limitations to the experiment. Things like what were the limitations of the equipment that we used, the setting that we used, okay? So things like that. And then just some notes as you're writing these labs, please make sure that you write organized and neat. Make sure to label each section, which one is the data table, the calculations, the results, and the conclusion. Okay. A mistake a lot of students make is to put the data and the results in the same table. Those need to be in two separate tables. The data comes before the calculations. The results come after the calculations. Because remember, the results are the answers to your calculations. Your data are the numbers that you collect. Make sure to include all the units when necessary. Note correct significant figures. This is probably the place that students lose the most number of points all semester. Make sure to show all of your calculations and all the work that you do for the calculations, and to write a well thought out discussion. Okay.